So here we have a chemical reaction for the formation of methane from the elements in their standard state. You can see carbon is in the form of graphite. Carbon comes in a couple different forms called allotropes. So you have graphite, you have diamond. The most stable state is graphite. In order to find delta G of the reaction, you first have to find delta H and delta S of the reaction. And you might say, oh, well, we're given them right here. Careful, you're not. You're given the delta H of formation for each of these components in a reaction, and you're given the absolute entropies for each of the components of the reaction. So you first have to do calculations to get these values. Then it's a quick plug and chug. Okay, so let's work on getting the standard heat of reaction first. The standard heat of reaction is going to be summing up the heats of formation for all your products and subtracting from that the sum of all your heats of reactions, heats of formation, for your reactants. Okay, so the product is going to be negative 74.9. Remember, if you had a coefficient out there, you'd multiply it minus, oh, look, this is pretty nice. These guys are 0 because they're in their standard states. So it's just going to be minus 0. So therefore, your enthalpy change for the reaction is simply negative 74.9 kilojoules per mole. So we got that one pretty easily. So now we're going to do the same thing for the entropy change of the reaction. We're going to sum up the entropies of the products, and we're going to subtract from those the sum of the entropies of the reactants. Now here we do have values for everything. So our product is the CH4, so that's positive 186.3. Do watch your units here. They're just joules per mole over Kelvin, so we are going to have to do a unit conversion in the end. Subtract from that, our graphite is positive 5.6, and then we'll add to that 2 because we have a coefficient of 2 in front of our hydrogen. So 2 times positive 130.7. Okay, so you can pause to get that calculation completed. I got an answer of negative 80.7. My units are joules over moles Kelvin. Remember that entropy has temperature in it. Okay, you can see I changed it into kilojoules per mole Kelvin by dividing by 1,000. And then up in our delta G equation, I substituted in the temperature in Kelvin, which was given in the problem. And then I put in our newly found change in entropy of the reaction. So lastly, we just have to do our arithmetic. You can see that Kelvin cancels. So we're subtracting units of kilojoules per mole, which is, it's important to have consistent units. So when we do this, we get a negative 50.9 kilojoules per mole for this reaction. So that's the math. What does it mean? The fact that this is a negative value means that it's a spontaneous reaction. So it's going to happen without outside influence. It's also known as thermodynamically favorable. That's the term the College Board prefers these days, but you can still use spontaneous. We also know that the delta H is actually negative, so that's a decrease in entropy. And this one will be hard to predict because you're creating a more complicated substance here. It is a gas. You're creating it from 2 moles of a gas, but then also from a mole of a solid. So this would be a really hard one to predict the sign of entropy. But you can see when you crunch the numbers, you get a negative value. And it's a relatively small entropy change. And you can also see that you get a negative value for delta H, meaning that it is an exothermic reaction when we form the methane.